Okay, we are going to do some Chapter 1 selected problems. This is Chemistry 101. It says convert each of the following values to scientific notation. Now, scientific notation is helpful, especially when you have big numbers. So for A, you just imagine that the decimal is there, and then you're going to have to, for scientific notation, the number decimal times 10 to a little number. Now n has to be a number 1 through 9, and little n is the number of places you had to move the decimal. Now, if your little n is negative, that means the number is actually smaller. The actual number is smaller than 1. And if it's going to be a positive exponent, then the number is going to be greater than 1. So you see that 29,500 is greater than 1. And so if we move this decimal here, we're going to have to move it 1, 2, 3, 4 places. So 2.9500 times 10, we moved it 5 places. So you see that now the decimal here is between the 2 and the 9. And we moved 1, 2, 3. Did we move it 5 places? Okay, wait. 1, 2, 3, 4. We moved it 4 places, didn't we? So, well, let me erase this. Let's see. Well, just mark it out there. Okay, so let's count again. 1, 2, 3, 4. So 2.9500 times 10 to the positive 4. That's the correct answer for scientific notation. And you see that the little n here is a positive value because 29,500 is greater than 1. Okay, let's do B. Now this is a small number, right? So we're going to have to move the decimal how many places? 1, 2, 3, 4, 5. So this is 8.2 times 10, 1, 2, 3, 4, 5. It's going to be a negative 5 because that number is actually small. So when you have to get this number out of scientific notation, you would move it the other way, and the negative tells you to make it a small number. So you would do 1, 2, 3, 4, and there's your fifth. So this is how you take it when you have the scientific notation. You have to put it in the actual number. 1, 2, 3, 4, 1, 2, 3, 4. Okay. So the C, as you see, is a large number. So this is going to be a positive little n exponent. And so it's going to be 6.51. And then let's count how many decimals. 1, 2, 3, 4, 5, 6, 7, 8. Times 10 to the 8th. And so if you were to move this out of scientific notation, you would count 8 movements, and it would go to the right to make it a big number. So 1, 2, 3, 4, 5, 6, 7, 8. And you can count 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Okay, so D, is it going to be a positive exponent or negative? Yeah, this is going to be a negative exponent. And you move the decimal 1, 2 to get that number in between 1 and 9. So 1.00 times 10, 1, 2 to the negative 2. Let's go on to the next question. We have 11 problems to work. Convert each of the following values from scientific notation to decimal form. Okay, so now we're going to do the reverse, but we were kind of doing that before. So the negative exponent tells you want to move the decimal here to the left to make it a smaller number. So 1, 2, 3, 4, 5. So, and then you can always double check it. 1, 2, 3, 4, 5. And is that number smaller than 1? Yes. So there's your negative exponent. Okay, what about B? 1 times, this should actually be 1.0, but sometimes you'll get it like that, to the 10 to the 7th. So let's go 1, 2, 3, 4, 5, 6, 7. And then you can just check it. If this is your decimal, 1, 2, 3, 4, 5, 6, 7. And so you're moving the decimal there. 7 is a positive exponent, so yes, you made it bigger. Let's see what that is. I think that's 10,000 or 10 million maybe. Okay. C, positive exponent here to the 5th. So 4, 5, 3. That moves it 1, 2, 3, 4, 5. So there you go. And then you can always check it. 1, 2, 3, 4, 5. That's a big number. D, we're going to go smaller number. You got a negative exponent. So 0.0061. And let's count that 1, 2, 3. So that's correct. For each of the following, carry out mathematical operations. Okay. So you work the ones in parentheses. You can get your calculator out. I use a calculator for the multiplication. And you need to get the TI 30 X or something in the 30s. Non-programmable calculator. You need to be practicing it because I've seen just 2 different calculators have to do scientific notation differently, and you don't want to be doing that on the exam. So 3.1, 3.1 raised to the 5th power. No, that's not right. 3.1, mine's, so for my calculator, I type in 3.1, and then I have to do the EE, which is on the second function. And so I do second EE, and then I put in 5. Okay, and then I equal that, and then that gives me 3100000. 1, 2, 3, 4 zeros. And you can see that's right. And then I multiply that by 2.0 second e to the negative 2. And so that multiplies. And so A becomes, on my calculator, 6200. And now, when you do mathematical operations, you want, for multiplication and division, you report significant figures. So these are the numbers we write down for my calculator. Those significant figures for multiplication and division are the least number. So here you have 2 sig figs, and we'll talk about that a little bit more. And here you have 2 sig figs. Here you have 2 sig figs. And they want to report the answers in scientific notation. So this would be 6.2 times 10, 1, 2, 3. That would be a positive 3. So that would be A. Okay, B, we take 2.8 second E to the negative 4th. And then that brings that out at 0.00028. And then I'm going to divide that by 9.6 second E to the negative 2. And my answer is going to be 0.002916667. That's what I see on my calculator. But you see, this is 2 significant figures, and that's 2 significant figures. So I only want these 2 here. So we're going to move that decimal to get it into scientific notation. 1, 2, 3 places. So our answer is going to be 2.9 times 10 to the negative 3, because this is a small number. We want negative exponent. Okay, let's do C. 8.5 second E to the 5th minus 3.0 e to the fourth, and that gives me 82000. Okay, so I have 4 zeros, and I need to get this in scientific notation. You notice this is we're going to move that 1, 2, 3, 4, 5 places. 8.2 times 10 to the positive 5. Okay, and then here we have 8.44 second e to the fifth plus 1.2 second e to the fourth, and that is 856,123. And I need to get that in scientific notation. That's a big number, so I need to move that decimal 1, 2, 3, 4, 5. 8.56 times 10 to the fifth, which is okay. Technically, this has 3 significant figures. This has 2. When you do addition and subtraction, you have to do the least number to the right of the decimal. We'll talk about that in a future slide. This one has 2. This one has 1. So we'd have to round this to an 8.6 times 10 to the fifth to be perfectly correct. So we're going to move that. Okay, determine the number of significant figures in the following. So how I do significant figures is I memorize this rule. Okay. Do not count zeros to the left. Okay, of decimal. Now, they are insignificant. So let's talk about what insignificant means. It means they're not important. Have you heard that Beyonce song, to the left, everything you own to the left? Well, that's not important, right? She's telling her insignificant other, because she's breaking up with him, to move all their stuff to the left, in the closet to the left, and not important. Significant digits are the important ones, and they're the reportable ones. So when you get a number like this, so you have to count all numbers. All numbers are like, if a number would be 1 through 9. Okay, zeros between a number is important. You count those. And zeros to the right of a number is important. Okay, so you got to count those. But we do not count zeros to the left. Okay, so here we would count these here. Okay, so we would count those, and so we would say the significant numbers are 3, because that's a 0 to the right, and there's 9. So basically I take my eyeball and I look, and when I scan for the zeros, I go from left to right, and I start counting when I first see a number. So see, I'm scanning here, and then I'm going to start counting right there. Okay, so my eyeball looks at B, and I see the 1, so I have to start counting. We count all zeros in the middle, we count all zeros to the right. So what would that be? 1, 2, 3, 4. 4 significant figures. Here are my eyeballs scanning, and I'm going to keep going until I come to my first number. And so the answer would be 2. Here are my eyeballs looking. Now, significant figures in scientific notation, you'll always have to start with an n of 1 between 1 and 9. So you're always going to count whatever that is, because any zeros will be in between or to the right. So this will be 3. And sometimes you'll want to report things in scientific notation so you can get those significant figures correct. Okay, express the answers to the following operations with the proper number of significant figures. Okay, this is where I was talking about earlier. When you do multiplication and division, it's the overall least number. We're going to do sig figs like that because it's a long word. So what's that mean? Well, here this number has 2 and this number has 4. So the least, when you report it, so you get your calculator out and you type in 1.2 times 1.216, and I get a big number, 1.4592. Now, I need to do the least, so I need to report this to 2 sig figs. So that means I need the 1.4, but now do I report that as 1.4? Well, I got to look at the number before the 4, and if it's a 5 or greater, I have to round up. Okay? If it's less than 5, then the 4 stays the same. So it's not 1.4, I have to round that, so it's 1.5 would be the answer. All right, so the B is also division. So we have 3.000 is 4 significant figures, and 2.0 is 2 significant figures. So the least number of significant figures is 2. So I'm going to type in 3.000 divide by 2.0, and I get 1.500000, lots of zeros. And I say, okay, I need to report it to 2, so I'm going to report that 1.5, and because this is a 0 right here, and the 5 stays the same, so I don't have to round up. Okay, now C and D, you're dealing with addition and subtraction. Okay, so when you're dealing with addition and subtraction, it's the least number of sig figs to the right of the decimal. So you see here, multiplication and division, it was the overall. But here, so what I like to do when I do multiplication and division, I actually line it up. 41, line up the decimals, 0.314, and then I subtract 41.03. And then I say, okay, how many to the right? 3 sig figs here. And here's 2 sig figs. So my answer needs to have 2 sig figs to the right of the decimal. So then I can use my calculator, 41.314 minus 41.03, and I get 0.2840. And then I say, okay, I need these 2 significant figures, and does the 8 stay 8, or does it go to 0.29? Well, I have to look at the 4. The 4 is less than 5, so it stays 8. 0.28 is my correct answer. Okay, D is addition. So 1.6 plus 1.15. This is 1 sig fig to the right of the decimal. This one is 2 sig fig. So, and I get my calculator out, 1.6 plus 1.15, and I get 2.75, and 1 significant figure to the right of the decimal. And so do I want that to be 2.7 or do I want it to be 2.8? I want it to be 2.8 because the 5 will round up. Okay, so this is the rounding of each of the following numbers to 3 significant figures. So we'll highlight the 3 here. 1, 2, 3. And then let's look at the 2. Well, So if it's 5 or greater, we're going to round up. If it's not, then it stays the same. So that is a 2. 2 makes it stay the same, so this number is 1.21. All right, so here, these are the 3 numbers because the 0 in the front doesn't count as a significant figure. So now we have to look at the 5. What's the 5 going to do to the 4? It's going to round up, so 0.205. That's what you would report. Here we have, these are our 3. We're going to look at this 5. The 5 is going to round up the 3 to the 4, so this is going to be 1.84. And then our next problem, we don't count the zeros in front, so we're looking at these 3 here, and we're going to see about the 1. Is the 1 going to keep the 0 the same or round up? It's going to keep it the same, so 0, 0, 7, 1, 0 is your answer. Carry out the following conversions. Report answers to the correct number of significant figures. Okay, this is using the metric system. So on the metric system, you need to memorize what the prefixes mean. So let's look at the prefixes that I think are important. So the base unit will be like a mass, meters, grams, liters. So these are no prefixes. They're just single letters. Okay, and we call that the base unit. And now the prefix tells you how many are in something. So your prefix can either be smaller than the base unit or it could be larger. So smaller would be a deci, we'll just use meter, deci, D, a centa, C. And they're all lowercase letters. Milli is an M, micro is a little cursive U, and then nano is N. Okay, and these are all smaller. So what does that mean? Okay, well, you have a penny and you have a dollar. Which one's bigger? So the dollar is the bigger and the penny is smaller. So 100 pennies will make up $1. Could you say, what if you got these numbers incorrect? What if you said 1 penny equals $100? And so you know that's not right. So what you'll see is the bigger number always goes with the smaller unit. And you know a penny is smaller unit than dollar. And then you have to memorize, what does it mean? Well, 100 pennies and $1. So you've been doing this all your life. So here you have to memorize that these little prefixes, D, C, little m, micro m, and n are smaller than the base unit. And then you got to memorize what they mean. So deci means 10, centa, like a century, means 100, milli means 1,000, micro is 6 zeros. Okay, so you got 3 zeros, 6 zeros, and then nano is 9 zeros. And you got to memorize that. Okay, so let's just work with the smaller ones for now. And here we have 36 millimeters to meters. So you do 36 millimeter, and then we're going to do this dimensional analysis, millimeter to meter. And then in this dimensional analysis, we're going to put what the prefix means. So what does the prefix mean? Well, milli is small, and so there's 1,000 millimeters equal 1 meter. And that's just something you memorize, just like 12 eggs are in 1 dozen. So you got the bigger number with the smaller prefix. And so now you can put 1,000 here and 1 there. And that tells you got to divide that. Whenever it's on bottom, you divide. So you would take 36 divided by 1,000. And so this is 0.036 meter. Now, what's 5 divided by 5? It's 1. 10 divided by 10 is 1. So whenever you take a thing by itself, divide by itself, it's 1. Well, what's 20 times 1? It's 20. So what this is doing is it's applying that math where when you do units, what you're doing is millimeter divided by millimeter cancels out because it's 1. And so what we are going to do on these, we'll always take whatever the letters are and we'll copy them on the bottom. And that way we get rid of them. So that's the answer for the first one. Okay, let's do B. So you have 0.000450 centimeters. Now I want you to go to the base unit first. So we don't want centimeters, so you're going to put centimeters on the bottom. And then we're going to go to the base unit. Now in these little boxes, these little square boxes here, you only want 1 unit, always, okay? So I see people make mistakes like that. All right, so let's continue on. So that will cross out centimeters. That gives us meters, and we need nanometers. So we don't want meters, so we're going to put meters on bottom, and then we're going to go to nanometers. Okay, so what's going to happen then? Centimeter divided by centimeter is going to cancel out, and meter divided by meter will cancel out, and we'll be with nanometer, which is what we want. Now we have to memorize how many centimeters are in 1 meter. So 100 centimeters equals 1 meter, because that's what it means. So the 100 goes with centi and 1 goes with meter. Okay, here, nana is 9 zeros. And so we have 9 zeros, nanometer equal 1 meter. And so you put 9 zeros there, and then 1 there. Now you can get your calculator out. You type in 0.000450 divided by, we just go from left to right, divided by 100. And then you take that number times the 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you get an answer 4500. 4,500 is your answer. And it says to report to the correct number of significant figures. So this is where you want to put it in scientific notation. So you would do 4.5 times 10 to the third. All right, so we're going to, we can add some space here. Let's move that out of the way. All right. Okay, so here we're going to go from grams to pounds, and that means you need to look in your book and your conversions. For these kind of conversions, I would give them to you. On your test. The metric units, the metrics I expect you to memorize. So I am looking this up right now. Let me look in your book. Usually you have a list of conversions in chapter 1. Okay. Yeah. So we have 453.6 grams equals 1 pound. So you want to take 236.504 grams, and then you want to make the dimensional analysis, and you're going to put grams on bottom and pound on top. And now you know to put the 1 with the pound and the 453.6 with the grams. And that's going to tell you to divide. So now you'll take 236.504 and you will divide that by 453.6 and you get 0.5213939298. How many significant figures do you want to report this to? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. The 2 keeps the 3 the same. So that is your answer, and you need to put your units of pound. Okay, D, your conversion factor that you need are, so these are all table 1.4 and table 1.5 in your book. Centimeters, so 2.54 centimeters equal 1 inch. So for D, 934 centimeters. And then you don't want centimeters, so you're going to write centimeters on bottom. And then you have this equals, so you can do this one here. 2.54 goes with centimeters, 1 goes with inch. And now you get your calculator and go 934 divided by 2.54. And that gives you 367.7165354. You need 3 significant figures. So the 367 is going to round up because of the 7, so this is 368. And then you put your units. In science, you should always have a number with a unit, and you will lose a point if you don't. Okay, E is a little harder, and let me tell you why. Because you'll see that 1 centimeter cubed equals 1 cc. Well, no, let's not do that. Let's see. We're going to use the same thing here. Okay. So do you see how you have 2.54 centimeters equals 1 inch? But here you want to cube it. So if you're going to cube it, you're going to have to change this. And so you're going to have to do 2.54 cubed centimeters cubed. Whatever you do to the units, you got to do to the number equals 1 cubed inch cubed. Now what's 1 times 1 times 1? That's 1. So that'll stay 1 inch cubed. But the 2.54, you're going to have to get your calculator out. 2.54, and you're going to have to cube that. So that's 16.387. And we have 3 significant figures, so 16.4. Well, actually, you shouldn't do that. 16.387. We wait to the end. Equals 1 inch cubed. So keep all your numbers until the end. Okay, so that's what you're going to need to use. So now you set it up as 24.5 centimeters cubed. You don't want centimeters cubed, so you put that on bottom, 2 inches cubed. And then you have to put your numbers in there. 1 with that and 16.387 with the centimeters cubed. And now you know you got to take 4.5 divided by 16.387. And that gives you 1.495087569 inches cubed. But you need 3 significant figures. You're going to have to round the 9 up. And that's going to round up to 1.50 because that rounds up to 10. So that's 0 and then causes the 4 to go to the 5. And that is what you would report, 1.50 inches cubed. All right, and the last one is F. All right, so let's do F. And you have 375 meters. When you have it like this, then that's over 1s. And when you don't see a a number there, you can assume 1 is that number. Okay, so here we are. Now, let's just do one at a time. Let's go meters to feet. So we don't want meters, so we're going to put meter on bottom. And I'm going to look at table 1.5 and I'm going to see if I can get a conversion for meters to feet. I don't see meters to feet. Let's see. Well, we got centimeters to inches. And then we have inches to feet. Well, no, we have, yeah, so 1 inch equals 2.54 centimeters. And then inches to feet, we have 12 inches equals 1 foot. And then for meters, you have 100 centimeters equals 1 meter. So to get rid of the meters, we can go to meters to centimeters. Let me show you what you do here. You just kind of like play a game here. Meters to centimeters. We don't want centimeters, we want feet. So we write centimeters on bottom. And then we have centimeters here that can go to inches. We don't want inches, we want feet. So you put inches on bottom and you say you got inches to feet. Okay, so that'll get us there. And then let's work on the seconds. So you keep going. So seconds to minutes. Well, seconds is on bottom, we don't want it, so we're going to put seconds on top. And can you think of a conversion? 60 seconds equals 1 minute. Okay, so then that puts minute on the bottom. Now you put in your numbers. So for meters, we have 1 meter, 100 centimeters. You have here 2.54 centimeters for 1 inch. Here you have 12 inches for 1 foot. Here you have 60 seconds in 1 minute. Now you can get out your calculator. You go 3, 7, 5. We don't divide by 1 because it'll just be the same, so we can just go on to the next bracket. Times, because everything on top is multiply. So top is multiply, bottom is divide. So times 100, and I have to equals mine out because that's what my calculator does. Divide by 2.54 equals divide by 12, and then multiply by 60. And so I get 73818.89764, and that would be seconds because meters cancel out, centimeters cancel out, inches divided by inches, feet stay the same, so it's feet per second, or seconds cancel out, and it's feet per minute. And that's what we wanted, feet per minute. See how, what are you left with? You're left with the feet, and you're left with minute, feet per minute. And we have 3 significant figures. So in order to report this, the 1's not going to cause the 8. We can't report it 738 because that's not the number. 73800. Well, the problem is you have to count those zeros as significant figures. So in this case, you're going to want to report it in scientific notation 7.38 times 10. 1, 2, 3, 4 to the 4th feet per minute. And then that would be the same thing as that, but it shows that you have 3 significant figures. All right, now we're getting into the periodic table. Hopefully I've given you this periodic table. You'll be able to use this. You want to classify the following as an element or a compound. So anytime I'm looking at formulas, I try to get the periodic table out because it kind of helps you answer the questions. So here we have oxygen. Well, there's oxygen. This is the periodic table of elements. This is a diatomic element. You could call this a compound because there's more than one, but usually what I classify as a compound is if you have more than one capital letters, because these are capital letters. Look at, like, okay, bromine. See, if you write bromine like this, I'm going to count it wrong. It's the first letter is capital, but the lowercase is small. Okay, chromium has a lowercase r. Titanium has a lowercase I, and that's important because this I, capital I, is iodide. Okay, so iodide. So capital letter means an element. So this oxygen is a diatomic element, and you're going to have to diatomic, yeah, diatomic element. And so what are your diatomic elements that you have to have memorized? I'll show you. There's 7 of them. So, so hydrogen, oxygen, um, nitrogen makes a 7. Fluorine, this is 7. Chlorine, bromine, iodide. So you got to include hydrogen over here, and then it makes a 7. You see how it makes 7? 1, 2, 3, 4, 5, 6, 7. So you can call that oxygen as an element. That would be an element. Now, how many letters are there? Capital letters. There's 2. Iron, Fe is iron, and oxygen would be oxide. You're going to learn naming. So that's 2 capital letters. That would be a compound. You're not going to find iron oxide, which is rust, on the periodic table. P4 is, you could call that a compound because it's more than one element. But also you could call it an element because it's found in nature as P4. So if it just has one letter, I'm going to let you go element or a compound. Helium would obviously be an element. There's only one capital letter there. Sodium chloride, you see how you have 2 capital letters, so that's an element. That's table salt. I'm sorry, not element, compound. That's a compound, more than one element. Water, 2 capital letters there. It's hydrogen. So 2 hydrogens are combined with 1 oxygen. That would be a compound, and it's composed of 2 elements, hydrogen and oxygen. Okay, a slice of Swiss cheese contains 45 milligrams of sodium. What is the mass in units of grams? So 45 milligrams of sodium. What is the mass in units of grams? Well, 1,000 milligrams equals 1 gram. So convert the 45 divided by 1,000. That gives 0.045 grams. What is the mass in units of ounces? Okay, so 45 milligrams of course you can go milligrams to gram, and then here 453.6 grams for 16 ounces. That's your conversion. So now you take 45 divided by 1,000 times 16 divided by 453.6. 0.00158730. You want 2 significant figures, 0.0016. That's going to round because of the 8, and that gives you that many ounces. What is the mass in pounds? So you go, just do it right here, 45 milligrams. You don't want milligrams, but you can go from milligrams to grams. And then here you can go from grams pound. So then you're going to put 1,000 milligrams for 1 gram. And then here you have 453.6 grams for 1 pound. You get your calculator out and you go 45 divided by 1,000 divided by 453.6. And that gives you 0.000099206. We want two significant figures, so 0.000099 pounds of Swiss cheese. Well, containing that much sodium. Sodium is Na on the periodic table. Okay, so our last problem is identify the following as a physical change or a chemical change. Boiling acetone. Okay, so I want you to know that physical change, okay, I want you to write all phase changes equal physical change. Okay, so if you have a phase change is physical. So when you boil something, what are you doing? Like when you boil water, it goes from a liquid, that little L there is liquid water, and you boil it, you go to a gas. And you know that. That's what boiling is, that process. That's a phase change. If you melt it, right? If you melt it, you go from a water solid. You see you're still H2O, H2O, H2O. You did not change the substance. What's actually happening when you're a solid, you're close together. So if these were all water molecules, are close together. And then what happens is you add heat, you add a little bit of heat here, a little fire, and then it causes these molecules to bounce off of each other. And they just spread further apart, but they're still the same. And then gas, you even add more heat. Okay, so we're adding more heat. And now it goes really far away. And that's what boiling does. You can even see the little bubbles on a pan of water because that's where the water molecule is at the surface and it wants to go into the gas phase. So boiling acetone is like fingernail polish remover. So boiling would be physical. Okay, dissolving oxygen, gas, and water. Well, if you have water and you have oxygen gas, and you put them together, that's a mixture, do you still have water and oxygen? Yeah, that's like, think about carbon dioxide in a Coca-Cola. Yeah, that's a carbonated soft drink. So that's carbon dioxide gas in the soft drink. So you can put oxygen and water. It's really important for fish and wildlife to be able to breathe the oxygen. And that's just a mixture. So, but the things stay the same. So that would be a physical. If it stays the same. Burning. Gasoline. Well, that's different. Gasoline is C8H18. And you combine it with oxygen, and then you have a reaction. These are the reactants. That's what you start with. And then they produce a product. And the product for this is called combustion. Okay? And that's CO2 gas plus water liquid. And that's always going to be your products on a combustion reaction. When we eat our food, what do we inhale? Breathe in, breathe deep. We're inhaling oxygen. Exhale. We're exhaling carbon dioxide. This is what we do for energy. We do combustion reactions. Same thing as our car. So now you don't have any more. The oxygen combined with the carbon make carbon dioxide. The hydrogen combined with the oxygen to make water. You no longer have gasoline. It's gone. No more oxygen. It's all converted to these products. So that is a change in elements, compounds. That's a chemical. Conversion of ozone to oxygen. So ozone to oxygen. Your change in ozone is what protects us from the what do you call it? The sunshine. And so ozone goes to oxygen, and you'll learn how to draw these at some point in the semester. But the ozone actually is like protects us from the sun, the UV rays. Oxygen doesn't. If you want to read on about some stuff, we do have a hole in our ozone layer. That comes from chlorofluorocarbons. And these are in our refrigerant, a lot of like aerosol sprays. And what happens is they react with ozone. And so we have a hole in our ozone layer. So technically our UV rays are high. Okay, this is obviously a chemical reaction. So you're changing substances. So that's chemical. Okay, that wraps up chapter 1.